Hello and Namaste. In continuation with the linear programming problems, we are starting with the dual simplex method. This method is little bit of different than what we are doing it in a simplex method. The beginning is little different, but we will be following the same method what we have done it for the simplex method so far in the previous sessions. So how the approach is little different for this dual simplex, we will be going ahead with that and we'll solve the problems based on that as well. Now, the primal simplex algorithm, that is a simplex method or algorithm, starts with feasible solution and it will continue to be feasible until the optimum is been reached. So this is what we have seen. Feasible means all the XBs or the RHS side are greater than or equals to 0 that we have started with. Now the dual simplex algorithm start infeasible but better than optimal and remains infeasible until feasibility is restored. The dual simplex method starts with a better than optimal and infeasible basic solution. The optimality and the feasibility conditions are designed to preserve the optimality of the basic solution as the solution move toward feasibility. The starting solution is infeasible. This is very important. Starting solution, we are always starting for the dual simplex with the infeasible solution if at least one of the RHS or the right hand side of the inequalities is negative. So this dual simplex method will come into the existence only if we will be having few of the RHS or the right hand side of this particular inequalities are negative. Now for this particular dual simplex, again the same three types of steps are there. First is formulation, second is dual feasibility condition, third one is dual optimality condition. Now let us see what will happen in the formulation. The same thing, if the objective function is minimization type, then change it to maximization. This is what we are doing it from the beginning. Please do follow the I button so that you will understand what exactly I am discussing on here. So minimization type we are converting into the max type. All greater than equals to constraints to be converted to less than equals to constraint by multiplying it by -1. Then transform every less than equals to constraint into an equality constraint by adding slack variable. So here we are not using any surplus variable, we are making it slack variable. Now few of the books or few of the authors are saying that okay, first use the surplus variable in it and then try to make that particular constraint after the equality as multiply with that -1, so that that slack variable will convert, surplus variable will convert into the slack variable. To every constraint and assign a zero cost coefficient in the objective function. So this is what is a formulation. We'll go in detail with the help of example. Now dual feasibility condition is the leaving variable xb is the basic variable having the most negative value. If there is a tie, that can be broken arbitrary. If all the basic variables are non-negative, the algorithm ends. If all the basics, so that means we are starting with the xb less than 0. If at all we will reach all xb's should be greater than or equals to 0, then we have to stop, or this particular algorithm will stop at this point. Then the dual optimality condition, if all the values of xb greater than equals to 0, then the current solution is optimal solution, terminate the process. That means if we have got all the xb's greater than equals to 0, we will not be able to continue or start with the dual simplex method. If any xb is less than 0, then select the minimum negative xb and this row is called the key row. So if you'll observe in the simplex, we are always deciding with the Cj minus Zj with the most positive and incoming variable. That means that the variable which is coming into the basis. That means we have decided in the simplex method or a big M method, we have decided first key column, wherein in this case, in this dual simplex, we are deciding first key row. Then find the ratio, that is Cj minus Zj upon key row j, and key row j is less than 0. That means they are negative. Find minimum positive ratio, that means what, Cj minus Zj upon the key row j, and key row j is less than 0. if there is a difference between like positive Cj and the negative key row j, then we have to put a dash. Whatever the condition we have discussed on the theta or the ratio, that we are not going to consider the theta when it is a 0, when it is a negative, or when it is a infinity, we are not going to convert. We are not going to consider the ratio. The same case is over here. If the ratio is coming out to be less than 0, then only the Cj minus Zj upon key row j will be coming into existence. If at all this ratio is coming out to be either 0 or a dash, that is a negative, actually dash is nothing but a negative, or the infinity, that time we are not supposed to use this particular corresponding variable as the incoming variable. Find the minimum positive ratio. Again, it's a minimum positive ratio. This column is called key column. And then find the new solution table. So this is what is the procedure or the algorithm in short will work for the dual simplex method. Now let us start with the one of the example. Use dual simplex method to solve the LPP. Maximize Z with this subject to 1, 2, 3, 4, 5. Actually, in fact, 1, 2, 3, 4, and fifth is a non-negativity constraint given to us. Now, what is this in the formulation? If you'll observe here, we have to understand first the objective function is from min to max we need to convert, but it is already maximization given. Then all the greater than constraint should be converted to the less than constraint by multiplying with -1, and then in the less than constraint we have to add or we have to introduce the slack variable. That is what is known as the formulation for this. So now we have to formulate this particular question by using the standard form of the LPP. Again, because it's a maximization, we need not to convert this into max because it's already been given as maximization. Then subject to the first constraint. Now if you'll observe, the first constraint is of greater than or equals to. So what we have to do it, we have to multiply this constraint by -1 throughout. We will be getting the constraint as -x1 -x2 plus s1, because it's less than or equals to getting converted with -1. As this is a less than or equals to constraint, we have to add the slack variable into the LHS side, the left hand side, and that's the reason there would be a first slack variable will come into the picture in the first constraint. Then the next one is, it is already less than or equals to, so no need to make any changes in the constraint. So adding the slack variable in the LHS, we are getting x1 plus x2 plus s2 is equals to 7. Third is again a greater than equals to, doing the same thing what we have done in the first case, multiplying the third constraint with a minus sign and then adding the slack variable in it as a s3, will be getting the equality. Last is x2 is less than or equals to 3, means what? x2 plus s4 is equals to 3. We do not have any greater than or equals to constraint in the last one, fourth one, so we have to go ahead with this. And then all of them with the non-negativity constraint, and then adding all this s1, s2, s3, s4 in the objective function with the 0 cost to all these slack variables. Now moving ahead with this, if we wanted to, now this is what is the standard form for this particular dual simplex method, we have found it out. Now if we wanted to convert into the table, we can have it in this way. So this is what is the standard form of this particular equation got. Now we have to form the basic variables. Now basic variables, to get this s1, s2, s3, s4, we have to put x1 is equals to x2 is equals to 0 as the basic variables, or you can say the variables which we will be taking the value as 0. After putting these values in first, second, third and fourth constraint, we are going to get this equations. So S1, the value of S1 from the first constraint is nothing but S1 is equals to -1, S2 is equals to 7, S3 is equals to minus of 10, and S4 is equals to 3. So with this basic, but it is not feasible. This is a infeasible solution or not feasible solution, because we are getting that as minus values in the basis. You can say that otherwise the variables are taking the negative values in the basis over here. Now moving with the first constraint, you need to just transform this particular what we have done into the simplex table. So this is what we are going to do it here in this case. Then the RHS is -1. Then we have to go ahead with this 1, 1. This is 0, 1, 0, 0, 7. Then the third constraint -1, -2, 0, 0, 1, 0, minus of 10. Then moving ahead with the fourth one, that is we do not have any x1 in the fourth constraint, so would be the 0, 1, 0, 0, 0, 1, and then it is equals to 3. So this is what is we got it as the transform this particular table in the tabular form, this particular constraints into the tabular form here in this. After transferring this constraints in this table, we can have this RHS minus 1, 7, minus 10 and 3. So we have to look at the least negative number over here, that is this is at the 10. That means we have to first decide the leaving variable. So S3 is going to leave the basis. S3 is going to leave the basis. Now which variable is going or entering in this, that is getting decided by the using the value of thetas. Before that we have to go ahead with the Cj minus Zj. Now this particular third row would become as the pivot, or you can say key row. Third row as a key row. Now looking at the Cj minus Zj, what we have done in the same way, that will be calculating the Cj minus Zj the same what we have done it so far. Please follow the I button how we did the calculate the rest of the things. So now I'm putting the value directly over here, because 1, 2, 3, 4 all of them the CBs are 0 over here. So the values would be same as that of CJs. So that is the values are coming out to be this. Now theta is nothing but we have to take the Cj minus Zj value of particular column and the particular this number, that is the value of this particular value, and this is nothing but the key row j. So if I wanted to have this j, that is a 1, C1 minus Z1 and the theta corresponding to that, so that would be nothing but minus 3 divided by minus 1. So it's nothing but minus 3 divided by minus 1, which is coming out to be 3 here. Then the next value is minus 2 upon minus 2, because we are taking this minus 3 upon minus 1 here, minus 2 upon minus 2 here, that is coming out to be 1. Then this is nil, or you can say 0 here. This also 0, this also can be written as nil or 0. So what we have to do the same thing. Same thing is least positive number we have to take it, and that variable will get into the basis. Now if you observe here the second, so this is the one which is the corresponding to the x2. So this particular variable, that means x2 is getting into the basis and s3 will leave. So this x2 will be getting into the basis, wherein in place of the s3 in this particular value. Now if you calculate the value of z over here, z for this particular step or the initial step would be 0, because all these basis elements have the coefficients as 0. Moving ahead to the next value, I have kept the same thing what we have done it in the first case. Now again the same thing we have to follow it. I have written our R1 old, R2 old, R4 old, and as this is R3 new, we have to convert this minus 2 into 1. That means what, we have to divide the entire row, that is the third row, with minus of 2. We have to divide that with the minus of 2. So that third row will become here 1 by 2, then it is 1, 0, 0, 1 by 2, then 0, and that will become here minus of this would be what would be that, that is equals to minus 10 upon minus 2, that is equals to 5. Let me write down this is directly over here. Then if I wanted to write down this R1 old, we have to convert this minus 1 as 0 using this one. So the transformation would be R1 old minus, this is R3 new. So R3 new, because it's minus 1, this is plus, so we need to have this addition. So R1 old plus R3 old will give you the first row. That first row becomes here minus 1 by 2, 0, 1, 0, minus 1 by 2, 0, and this RHS becomes 4. Same thing with S2. I'm writing this steps now. I'm going a little fast over here because we have already had this discussion before in previous cases in detail. Please do follow the previous sessions. I am concentrating here on making you understand with the dual simplex. So this is the same way what we have done it so far in the case. So we are getting in this way. Again, we have to decide which is the negative RHS over here, and that is also least negative. But we do not have any other negative than this -2. So this -2, that means corresponding to this S4 variable will leave the basis. This will leave means this particular fourth row becomes here the pivot or a key row. Fourth row become the key row of this particular first iteration. This is the fourth. So this is key row. Again, Cj minus Zj we need to calculate here. We have got change in the x2 because the x2 get into the basis as on in place of the s3. That's the reason the Cb has changed from 0 to minus of 2. Because of this fact, we are having the Cj minus Zj different than this -3 -2 0. So what would be them? They would be 4, sorry, they would be -2, then it would be 0, 0, 0, then we'll be having it here minus of 1 and then 0. These are the values. Now based on this particular, Z can be calculated as minus of 10 and Z can be calculated as -2 into 5 because other 3 variables have the 0 as the coefficient or CB as that. So we can have this as, so Z equals to -10 in this particular step, or you can say first iteration. Now how that row or a ratio can be calculated? Ratio is -2 upon minus of 1 by 2. So it is -2 upon minus 1 by 2, that will gives us plus 4. It's plus 4. Then it would be 0 here. Then it would be 0. It would be 0 because these elements are already 0. Now again, minus 1 upon 1 by 2, that will gives us the value which is negative. We do not have to calculate that. As I've told you, 0, negative as well as the infinity we are not going to consider. So we have to just put the dash over here. And the S4 is coming out to be 0. That's the reason we'll be having this particular value as this one. Now again we need to calculate, or we need to take the ratio which is least positive, that would be 4 will get into the basis, and in place of S3 we'll be having X1 in the basis. Now let us move ahead and check. Sorry. So this is the table what we have left it from the last, and if you'll observe S1, S2, X2 and X1, they are the basis elements. The CBs are 0, 0, -2 and -3. Now we have to calculate this minus half needs to be 1. Because I need this is minus half needs to be 1 over here. That means what we have to divide this entire row by minus of 1 by 2 again. That will gives us this element as 1. Then this is 0, 0, 0. That would be -1, and that would be the another one is minus of 2. Again, using this one, we need to make this minus half as 0, half as 0, this half as 0. So using this transformation, I'm just directly writing the steps. 0, 0, 1, 0, -1, -1, and this is 6. Next is 0, 0, 0, 1, 1, 1, 0. Next is 0, 1, 0, 0, 0, 1, 3. And this is last row which we have got it as the 4 over here as the RHS. It's very simple to note it down because it's a -2 over here. We are dividing the entire row, fourth row, with minus of 1 by 2. So obviously it is going to come as 4 over here. Now based on this, if you'll observe in the RHS there is no negative XP, or you can say no negative RHS present here, or the solution present here. That means what we have got it here the optimal. Now you can check that with the help of Cj minus Zj also, whether this is really the optimal solution or not. How can we do that? We have to find out Cj minus Zj for all of them. Now x1, x2, they are the elements of basis, so obviously this is coming out to be 0 as I have told you last time also. S1, S2 is 0. Then we have got -3, -4. That means all Cj minus Zj, Cj minus Zj's are less than or equals to 0. So again this is actually, in fact, this is the stopping condition for this particular dual simplex method, because we do not have any other scope of infeasible solution present in the question. That's the reason we have reached here the solution with this. Now what is the solution? X1 is 4, X2 is 3, and what would be the value? What would be the value of Z that will give us the values of Z equals to? It is minus 3 into 4 plus minus 2 into 3. That would gives us the value as minus of 18 as the Z max. And if you'll observe the entire question at one go, you can easily check that this is what we are going to get it as the thing. Normally we do have in the simplex method the RHS present over here as the column, but here in the dual simplex we are having this that's ratio here in the row, or you can say in the at the last row of the table. So if you observe here, this is the rows we will be getting at the last step, and this is what is the answer. You can easily check this is the what we got it here. Now this is the self-observation slide, the favorite of mine. 1-2 questions along with the 2 answers given to you. Please do solve and get the practice for this dual simplex method. If at all any doubt, please comment in the comment section. Thank you. Happy learning.